Okay guys, I just finished watching the video about the polar coordinates. It was exactly really cool. I think I get the difference between rectangular x and y and polar r and theta coordinates now.
Yeah, same. Rectangular coordinates use the x and y axis, while polar coordinates use the radius and angle from the positive x-axis. So instead of moving horizontally and vertically, we rotate them and move outward.
Exactly. So a polar coordinates is written as r and theta, where r is the distance from the origin and theta is the angle in degrees or radians.
Right. And they mentioned that positive angles are measured counterclockwise, while negative angles go clockwise from the positive x-axis.
Okay, so let's try an example together. Say we want to plot the point 3 and 45 degrees. What would we do?
First, we draw the concentric circles with one radius 1 and one with 2 and one with 3.
And then, since the angle is 45 degrees, we draw a ray that starts at the origin and goes out at 45 degrees. That ray intersects the circle of radius 3, so the point is located there.
Perfect. Just like that, 45 degrees is in the first quadrant between 0 degrees and 90 degrees. So we know it's up and to the right.
What about something in radians like 3 pi over 4?
Let's convert it to degrees. So 3 pi over 4 times 180 degrees over pi is equal to 135 degrees.
135 degrees is in quadrant 2, between 90 degrees and 180 degrees. So, we got the radius 2 along with 135 degrees in line.
The point would land between the second and third circles, right at the second one.
Here, this is our plot for 2 and 135 degrees. So cool. How the direction change based on theta?
But the part that messed up with my head is a bit when r is negative. Like, say we want a plot with negative 2 and 60 degrees. How do we deal with that?
That part is tricky. Remember what the video said. When r is negative, we move in the opposite direction of theta.
So, for negative 2 and 60 degrees, we first plot 2 and 60 degrees, which would be in quadrant 1. But since r is negative, we go to the opposite side of that ray, adding 180 degrees to theta.
So 60 degrees plus 180 degrees is equal to 240 degrees. That's where the point negative 2 and 60 degrees ends up along the 240 degrees direction, radius 2.
Okay, let's try another one. Let's say negative 3 and 120 degrees. First plot is 3 and 120 degrees, which leads into quadrant 2.
Then for negative 3 and 120 degrees, we go to 180 degrees more. 120 degrees plus 180 degrees is equal to 300 degrees. So the point is at radius 3 along 300 degrees, which is in quadrant 4.
And the video showed how to represent the same point in different ways. So negative 3 and 120 degrees is the same as 3 and negative 60 degrees, negative 3 and 120 degrees, and 3 and 300 degrees.
It's like a secret identity. One point can have a multiple polar representations.
So to summarize, first is r and theta, second is r and theta minus 360 degrees, and negative r and theta plus 180 degrees, and lastly, negative r, then theta and 180 degrees. So as long as the new angle ends up pointing to the same location.
Let's test that with 2 and 30 degrees. What are the 3 other polar coordinates for the same point?
Alright, first one, 2 and 30 degrees, that's the original. The second one, same r, the theta is 360 degrees. That's equal to 2 and negative 330 degrees. third one, negative r, theta plus 180 degrees, that is negative 2 and 210 degrees. The fourth one, negative r, theta minus 180 degrees, that is negative 2 and negative 50 degrees.
Boom! It's 4 versions at the same point.
Now let's plot all four on the same polar grid to visualize the real line at the same terminal point. We will see that we're just approaching the point from different paths.
What I really like was how flexible polar coordinates is, or when representing angles. Like, you could use 360 degrees or 300 negative 300 degrees or even 2 pi and still get the same direction.
True, and sometimes it's better to use radians in trigonometric functions, especially for calculating arc length or area of sectors.
That reminds me, polar coordinates are super useful in real-life applications like navigation, robotics, electrical engineering, and even modeling spiral galaxies.
Right, anything with circular motion or radius symmetry makes more sense in polar form, like describing the location of a planet in orbit.
So, if someone gives you arc and theta and asks for rectangular form x and y, we can convert using x is equal to arc times the cosine of theta and y is equal to r times the sine of theta.
And to go from rectangular back to the polar, let's use the r is equal to square root of x squared plus y squared, and theta is equal to tan inverse of y over x. But we have to be careful about which quadrant we're in.
Definitely, because inverse tangent doesn't always tell the whole story. Sometimes we need to adjust theta by adding 180 degrees or subtracting based on the quadrant.
Now let's try this one. Convert 3 and 45 degrees to rectangular.
We'll use x is equal to 3 times the cosine of 45 degrees. That's equal to 3 times the square root of 2 over 2, approximately 2.12. And the y is equal to 3 times the sine of 45 degrees. That's equal to 3 times the square root of 2 over 2, approximately 2.12. So it's approximately 2.12 and 2.12.
Nice! That's perfect example of how polar and rectangular coordinates relate.
Okay, last challenge. Find all four polar coordinates equivalent to 2 and negative 45 degrees. Use theta between negative 360 degrees and 360 degrees.
So let's go. First is 2 and negative 45 degrees. The second is 2 and 315 degrees. Since negative 45 degrees plus 360 degrees. Then third is negative 2 and 135 degrees. Then add 180 degrees to an angle. Lastly, negative 2 and negative 225 degrees. And subtract 180 degrees from negative 45 degrees.
Boom! Got him! Awesome work, everyone! I feel like we really get this now. Next time, let's try plotting polar equations like cardioids and spirals.
Yes, and maybe even converting equations between polar and rectangular forms.
Agreed. Today was all about understanding the coordinate system. I'm actually excited for what's next.